Let's see Proton NMR. So NMR is a technique that is used to determine the different chemical environments that hydrogen atoms are present in a molecule. So for example, if you have these three different molecules, if we look at methane molecule, so you have these 4 hydrogen, they are all bonded to a carbon. So it's hydrogen bonded to a carbon. So these 4, we say that they are equivalent. So these are in the same environment. If we look at the second molecule, so here you have a hydrogen which is bonded to a carbon. So hydrogen bonded to a carbon, and the carbon is bonded to a CH2. So these 3, they are in the same environment. But when you look at this hydrogen, here it is bonded to a carbon which is bonded to a CH3 and another CH3. So these 2 are in the same environment. And if you look at the other carbon here, so you have hydrogen bonded to a carbon which is bonded to a CH2, which is the same as the first group of hydrogens here. So we have 2 different types of environment. One type of environment in red, which are equivalent, and one type of environment in yellow. So here you have 2 different environments. If I look at the third molecule here, I have 1, 2, 3 hydrogen. So these 3 hydrogen, they are bonded to a carbon which is bonded to a CH2, which is again bonded to a CH2OH. And then I have another hydrogen environment. So this one is bonded to a carbon which is bonded to a CH3 and which is bonded to a CH2OH. So these 2 are different. And then I look at the third carbon atom. I have this hydrogen here and this one. So these, you have the hydrogen which is bonded to a carbon, which is bonded to an OH, and which is bonded to a CH2, CH3. So this is different from the other 2 that we had. And then I have one last hydrogen here. This one is different from all the other hydrogens. So this one is bonded to an oxygen atom. So NMR is going to allow us to determine how many different environments that you have in a molecule. So what happens is that the protons, the H1 protons, they can spin clockwise or they can spin anti-clockwise. Now, if you apply that molecule to an external magnetic field, the proton spinning anti-clockwise will produce a magnetic field. The proton spinning clockwise will also produce a magnetic field. But these 2 magnetic fields will align differently to the external magnetic field. One will align in the same direction, like here, and one will align in the opposite direction, like this. Now the change in spins from the normal state of the hydrogen to the spinning of the hydrogen, when there is a change in the spin, it's going to absorb radio frequencies in the electromagnetic spectrum. And this is what gives rise to peaks in the NMR, in the HNMR. So the HNMR gives us several information. It tells you how many different environments you have. So the number of peaks tell you how many different environments you have. So for this case, if you look at CH4, you're going to see only 1 peak because there's only one environment. Here you will see 2 peaks because there's 2 different environments. Here you're going to say 4 peaks because there's 4 different environments. The NMR is going to also give you how many hydrogens do you have in that particular environment. So you're going to have 1 peak, and the area under that peak is going to be 4, which indicates that there is 4 hydrogen. If we look at this one, here you're going to have, so 1, 2, 3, 4, 5, 6. So you're going to have 2 peaks with the ratio 6:2 because you have 6 protons in the red environment and you have 2 protons in the yellow environment. Then for this one, you're going to have 4 peaks, and the 4 peaks are going to be in the ratio of 1, 2, 3, 3:2, 2:1. So the ratio of the area under the peaks give us information of how many protons do you have in that particular environment. And then the last information is the chemical shifts. The chemical shift will give you an idea of the type of proton. So we have different chemical shift values for the different groups of protons. For example, the proton in a CH3 is going to absorb radiation of frequency different from the proton in a CH2. So they have chemical shift values that are specific. So all these chemical shift values are given in the data booklet. So the different types of protons and then the chemical shift value. So you can see it's slightly different. Now the chemical shift value is a relative value and it's taken with reference TMS molecule, tetramethylsilane, which is TMS. Now if you look at the TMS molecule, so in the TMS molecule, you see that all these hydrogen, they are all bonded to a carbon, which is bonded to a sulfur, and then to a CH3. So these all hydrogen are in the same environment. So you have many hydrogen atoms in the same environment. This leads to a very strong peak. Moreover, because of the unique type of environment of these hydrogen, it gives you a chemical shift value which is far, if you could say, far apart from the other chemical shift values that you get for other compounds. Therefore, the peak due to the TMS can be easily identified. And also TMS is inert, which means it doesn't react with the samples that you are analyzing. So when you will look at an NMR spectrum, you're going to see the TMS peak, which is just a reference peak so that we can give the chemical shift value of 0. Let's see this first NMR. So here you have 1, 2, 3 different peaks. 1, 2, 3 different peaks. So if you have 3 different peaks, means you have protons in 3 different environments. So the 3 peaks are in the ratio 1:2:3, which means that in the first environment you have 1 proton, in the second environment you have 2 protons, and in the third environment you have 3 protons. Now let's look at the chemical shift values. So this is around 1, this is around 3.8, and this is around 4. So already when you look at it, you should already be able to identify what it is. Normally, if you see a peak with 3 hydrogen and a peak with 2 hydrogen, normally it's going to be a CH3 and a CH2. And then 1 hydrogen means there is 1 hydrogen apart, separated completely to other hydrogens. So most probably it's a carbon attached to OH. It might be a proton in an OH. Let's check the chemical shift values. So chemical shift of 1 corresponds to CH3. Chemical shift of 3.8 corresponds closely to this one, CH2OR, or CH2, in this case OH. And then an R group connected to OH is in the range of 1 to 6, so this fits in the range. Let's look at the second NMR spectrum. So here we have 3 peaks, so means there's 3 environments. So in one environment you have 3 hydrogen, another one you have 2 hydrogen, and then you have a third environment with only 1 hydrogen. So 3 hydrogen, most probably it's going to be a CH3. 2 hydrogen, most probably a CH2, and 1 hydrogen, it could be an OH because there's just 1 hydrogen in it. So if we look at the structures provided, so it's for C3H6O, you have to change this. So this is another molecule, CH3, CH2, CHO. So if we look at here, if this was the answer, here you would get a CH3 and a CH3. These two are bonded to a CO. So here, these 6 hydrogen, they are all in the same environment. So you would have only 1 peak with integration 6, which shows that there would be 6 hydrogen. If we look at this one, there is 1, 2, 3, 4. So you see you have 1, 2, 3, 4. So this would give rise to 4 peaks of intensities, 2 is to 1, is to 2, is to 1. And the last one, you see you have, so CH3, CH2, and then CHO. So you see you have the CH3 here. So this is one environment. This is a second environment, and this is the third environment. So 3 peaks of ratio 3:2:1. So here that 1 hydrogen is not because of an OH, but it's because of the H in CHO. So it's still a hydrogen that's alone, and that's in a different environment compared to the others. So this is one way that you could answer it. So it produces 3 peaks, 1, 2, 3, due to the 3 different environments. The area under the peaks are in the ratio 3:2:1 due to 3 hydrogen in CH3, 2 hydrogen in CH2, and 1 hydrogen in CHO. You can also draw the diagram to show the different environments. So let's see our third spectrum. Whenever you see 3 and 2 together, most probably it's a CH3 attached to a CH2. Okay, so here you have an unknown compound, so there's 2 oxygen, so most probably a COOH. If you calculate the IHD, you're going to have 1. So most probably the double bond in the COOH. The peak at 11.7 ppm. So this peak has only 1 hydrogen. So most probably it's the peak due to the OH in the COOH. Here, distinguish between the spectrum of 1 bromopropane and 2 bromopropane. So first you draw the molecules. Let's try to spot the different environments. So I have these 2 hydrogen that are equivalent in the same environment. Then these 2. And then you have the CH3. So here you have so CH3 is bonded to a CH2, which is bonded to a CH2Br. Here you have CH2 bonded to a CH3 and a CH2Br. So these are different. Let's look at this one. So here you have two different CH3 groups. So you have one CH3 on this side and one CH3 on this side. But this CH3 and this CH3, they are both bonded to CH2Br, which means that these two CH3s, they are going to be in the same environment. And then you have one hydrogen here, which is in a different environment. So if you look at these two spectra, here you're going to have 3 peaks, while here you're going to have only 2 peaks. And here the 3 peaks are going to be in the ratio 2:2:3, and here you're going to have 2 peaks which are in the ratio 6:1. So that's it. With this we end with H NMR.